Uh, Hi, I hope you are doing well today. I will present a CVPR 2021 paper called TransGAN. Two transformers can make one TransGAN. Okay. Today we will briefly talk about not so detailed, but just in a simple way about GANs. And then we will talk about the universal model transformers. And then we will talk about the impact of transformers in computer vision, which is related to our paper. This paper. Also, we will talk about the methods and experiments and so on. So, as you all know, generative adversarial network has two narrow networks, which consists of generator and discriminator. Generator tries to minimize the log probability of its samples, which is being classified as fake by the discriminator. Also, the discriminator tries to maximize the log likelihoods for the binary classification problem, such as real or fake. As you see from the equation, it is the summary of the GANs. The first original GAN paper, they use the fully connected networks, but it just generate small images. When we evaluating the GANs, we use the IS and FID scores. IS is actually evaluate the diversity of the samples that's generated, and FID is actually sensitive to mode collapse. So after the first GAN, DC GAN was proposed by Radford et al., which who they used the deeper convolutional neural networks to generate the higher resolution images. And in the computer vision domain, GAN relies on the CNN-based generators, and discriminators are really successful. Also, convolutions with the strong inductive bias for the natural image contribute to appealing visual results, and that is empower the CNN architectures in GANs. Fundamentally, a convolution operator has a local receptive field, and hence convolutional nets cannot process long-range dependencies unless passing through a sufficient number of layers. That cause the loss of the feature resolution and fine details when generating the images or samples, and it's hard to optimize. That's why the authors ask a question: could we build a strong GAN completely free of the convolution, so that we will not use any more convolutions? The universal model is transformers. That's why they use the transformers for architectures for the computer vision tasks. Also, it has a really impact in the NLP community. There are two reasons why transformers has been used in computer vision. One is it has a strong representation capability and is free of human-defined inductive bias. In comparison, actually, CNNs exhibits a strong bias towards feature locality, and as well as the spatial invariance due to the sharing filter weights across all locations. Also, the transformers architecture is a universal models, and it becomes very powerful when you increase the data set, and it has a really impact on different benchmark and the community, such as cheminformatics and the other fields. What is transformers? As you all know from the deep learning courses, in the traditional, the transformers has consist of two blocks, encoder and the decoder. The main operator here is, as you all know, multi-head attention. The other is so common to us because we know the skip connection from ResNets. Here, the important point here is that positional encoding, since transformers is permutation invariant, and when you change position of a word in the machine translation, the meaning of the translation could be changed differently. That's why we use the positional encoding. In the multi-head attention, we have scale dot product attention, which is the basis of the attention mechanism. Q is the query, key, and value. This query is a vector, key is a matrix, and V is a value is a matrix. Actually, mathematically, this equation is summarized. This equation summarizes the attention scale dot product attentions. After that, we put into the multi-head attentions. As you all know, we concatenate all the head attentions and multiply with the parameters. Also, this parameter is actually is a model parameter, I think. And there's also another parameters for the head eye attentions for the each query, key, and value parameters. It could be seen from these equations. Related work in 2020, as far as I know, in October 2020, there was a paper was published from Google called Vision Transformers. In this concept, they used the transformers encoders with MLP. In this model, we have an image that's split into the patches, which represents as a word in the in the NLP tasks. Before put into the transformers encoders, the patches, let's say, have 16 by 16 dimensions. Before going to the transformers encoder, we unroll this image and multiply with the embedding matrix. After that, we concatenate with the patch embeddings and then put into the transformers encoder. Here we have learnable class embeddings, which is used for the classifications, and then we put into the transformers encoders, and then with the MLP we classify the image. Here an illustration of the vision transformers. As I said before, we divide it into the patches and then unroll it. It is the same pattern as I said before. So when comparing the results vision transformers, we could see that the position embeddings is learnable, and it is something like the convolutions. In the convolutions, we slice slice the kernels into the image, and we could see that this is it shows the positions of the each patch, and it shows that these patches are learnable. Also, in the convolutional neural nets, we visualize the image in the layers, and it seems really similar to the conv nets. Also, as a result, you see that in the image net, it is really competitive with the popular convolutional architecture ResNets, and also use it in other results. Another advantage is that we could see that it is computationally efficient with respect to convolutions. That's why transformers in computer vision is becoming how can I say the main operations, I could say. So in the TransGAN, we have two transformers, which is transformers, the generator and discriminator. These are consist of the transformers encoder. The operation here, we put the noise input into MLP, and we do the same thing in the positional encoding and the patch embeddings here as we do in vision transformers. And then we put into the transformers encoders. Here, this model is actually TransGAN is really computational efficient, because here we upscale the image. For example, in the ConvNet, we have a high resolution image, but less channels. When we go deeper, we have a low height and weight, but a big, how can I say, channels. And then we locally unroll this image in order to get high resolution images. So here we do the same things, but in an inverse way. We actually put a lower height and weight image with the high channel, and then we upscale this image. We actually get higher height and weight, but less channels. And then when we do the same things again, we get the same results. After that, this transformers encoder, we do the same positional encoding. Sorry, pixel embedding. I'm sorry. After that, we put in the linear unflatten in order to get the this image. After that, we put in the discriminator, which is same as in vision transformers. Here we just classify this image as a fake or real. So this is so similar to the vision transformers. The experiments, they do some data augmentation, and we see that TransGAN with the data augmentation, the performance is increasing, as you see here. They also training strategies, I could say, code training with self-supervised auxiliary task. Here, as you, this task comes for free, since we can just treat the available real image as a high resolution and downsample them to obtain a low resolution counter parts. This actually says that they use really unique strategy to train the GANs. For example, in traditional GANs, we have a noise image. We generate the image and put into the discriminator, and discriminator classify it as a fake or real. But here we have a data set, and with the super resolutions, we have a bigger high resolutions, and we downsample them to low resolutions in order to show the generator the low resolution image. And this is the actual first time, I think, showing the data set image to generator. At the end of the model, we have another loss functions from another loss functions from this co-training with self-supervised auxiliary task, and we have also again loss functions. We multiply with these loss functions, and we get a new loss functions. Also, this tasks enables to get the TransGANs to increase the performance. Locality aware initialization self-attention. This vision transformers authors observed that transformers still tend to learn convolutional structure from image. Therefore, a meaningful question arises: can we efficiently encode inductive image biases while still retaining flexibility of transformers? This means that we use the global transformers, but could we just use our models by not changing, but use in the local way? So they introduce a mask by which each query is only allowed to interact with its local neighborhoods that are not masked. It's something like in graph neural nets. We have each neighborhood. When we go to deeper, we have a larger neighborhoods as shown here. In the earliest stage, we have a fewer neighborhoods, but in the middle we go to deeper, and this unmasks diminished. At the end of the stage, we have full image. So they just introduced this mask. Different from the previous methods, during the training, they gradually reduce the masks until the diminishing, and eventually self-attention is fully global. There are advantages and disadvantages. During training, the mask reduced until diminishing it, and eventually self-attention is fully global. At first, it's most helpful, but when you training later, it can hurt the training stage. They consider this locality aware initialization as a regularizer that comes for early training dynamics and then gradually fades away. So they tried a lot of things. So it's time to scale up the large models. This is the depth of the transformers encoders, and this is the dimensions of the inputs. It shows that when we have higher dimensions, the capacity, the performance of the TransGANs are increasing, and we could say that the transformers has a universal model. That's why it's eager to data, more data, and more good performance for this model. As you can see, this is the generated image. Not, yeah, it's competitive actually with respect to other models. We will see this with the other models. There's also another study. They try to actually compare to CNNs and the transformers generator and discriminator. As a generator CNN and discriminator CNN, we could see that generator transformers outperforms very well, but this two generator transformers and discriminator is not doing well. But this model did not do data augmentation, so that's why the insertion score is lower with respect to others. So this is the comparison of the tables with the other GAN models. We could see that TransGAN is very competitive with other GANs. So as a conclusion, we could say that this is the first time that a GAN has no convolution and is just done by built purely transformers. And it is also memory-friendly generator. That's why it's the advantage of the transformers over the CNNs. Also, TransGAN can be effectively scaled up to larger models. This is another advantage. In the training technique, they actually tried data augmentation and showed that TransGAN can outperform with the data augmentation and multitask co-training for generator with self-supervised auxiliary loss and localized initialization self-petition. This is the last two ones are really unique techniques. We could say that. Also, as a performance, TransGANs highly competitive with state-of-art CNNs. So actually, this when I will finish my presentation. But there is also another thing that I would like to say lastly. Firstly, we have a convolutional neural networks, and everyone says that convolution is all you need. But after the transformers paper, attention is become our all you need. A couple days ago, another paper has been published by Google, and it says that MLP is all you need. It's the paper name, if you want to really read and look at the more details. The paper is MLP mixers. Do we need even attentions? So I would like to say that where are we going in the computer vision or in the deep learning? So thank you for listening. If you have any question, I'm glad to answer your questions.